In this final lesson of the momentum unit, we're going to talk about elastic and inelastic collisions. So let's consider two balls that collide and they bounce off of each other and energy is conserved. This is defined as an elastic collision. Another scenario, a piece of gum falls and hits the ground, not bouncing. Energy is lost. This is considered to be an inelastic collision because energy is lost. And what we're going to consider in our problems is a specific type of inelastic collision. This is when two balls collide, stick together, and travel together. So let's say I have a ball coming this way, a ball coming this way. They stick together like they were pieces of clay, and they travel together. Energy is lost, but this is called a perfectly inelastic collision, and it has to do with the fact that momentum is conserved. We'll talk about that in a minute. So first, let's consider elastic collisions. Elastic collisions are when two objects collide and bounce apart. In elastic collisions, momentum is conserved, so we can use the law of conservation of momentum, and kinetic energy is conserved. So let's do an example. Let's say we have a 50-gram marble moving at 2 meters per second, and it strikes a 20-gram marble at rest. After the collision, the 50-gram marble travels at 0.86 meters per second. What is the speed of the 20-gram marble after the collision? So after the collision, you see that both of them are moving to the right. Assume the collision is perfectly elastic and the marbles collide head-on. Head-on meaning we only have to consider the x direction of motion. They're only going to travel along the x-axis. So first, since it's an elastic collision, momentum is conserved and energy is conserved. So we'll start with conservation of momentum. Conservation of momentum tells us that the initial momentum equals the final momentum. The initial momentum is the initial momentum of ball 1 plus the initial momentum of ball 2. And the final momentum is the final momentum of ball 1 plus the final momentum of ball 2. Remember, momentum is defined as mass times velocity. So this is our initial momentum of ball 1, our initial momentum of ball 2, our final momentum of ball 1, and our final momentum of ball 2. We're going to plug in the values of the mass and velocity for each ball. And this is our initial momentum of ball 1. The initial momentum of ball 2 is actually 0 because it started at rest. We know our final momentum of ball 1, and we're trying to find our final velocity of ball 2. So this is the variable we're solving for. So now we can simplify this equation, combine terms, and divide by 0.02 kilogram to get velocity of ball 2. And we get the velocity of ball 2 is 2.9 meters per second. Now initially this large ball had a lot of momentum because it had a larger mass and it was traveling at 2 meters per second. At the end it had a smaller momentum because at the end it traveled at only 0.86 meters per second. So a lot of its momentum was transferred to ball 2, which is why ball 2 has this larger velocity of 2.9 meters per second. So that's an elastic collision. We also have inelastic collisions. An inelastic collision is a collision where, and the important point is, the energy gets lost. But the specific type of inelastic collision we're going to consider is a perfectly inelastic collision. In a perfectly inelastic collision, our two objects come together, they stick together, and they travel together with a common final velocity. In this process, our momentum is still conserved, and this is the key point for perfectly elastic collisions. We can use our conservation of momentum to find the final velocity. We also know that because it's inelastic, energy is not conserved, so you should expect that the energy initially is going to be greater than the final energy. Some of that energy is going to be lost, and that energy goes into when you combine these two objects, you can see one gets dented, so some of the energy is lost in the collision itself. So let's do another problem. Let's say we have a 300-gram bird flying along at 6 meters per second. It sees a 10-gram insect heading straight toward it with a speed of 30 meters per second. And in this picture, we put the velocity as negative because the insect is going in the opposite direction of the bird. The bird opens its mouth and enjoys a nice lunch. What is the bird's speed immediately after swallowing the insect. That's the first part. Then next, how much energy was lost in this collision? So since these two objects have come together into one object and now they're traveling with a combined final velocity, we can identify that this is a perfectly inelastic collision. And the properties of a perfectly inelastic collision are the momentum is conserved and energy is lost. So we'll start with, for the first part, finding the bird's speed after swallowing the insect. We're going to use our conservation of momentum. So it's our initial momentum equals our final momentum. The initial momentum of the bird plus the initial momentum of the insect equals the final momentum, which is a combined bird and insect, the momentum of both of them together. We combine, remember, P equals mv, so the initial momentum of the bird, the initial momentum of the insect equals the final momentum of the bird and the insect. We put in the values that we know. The bird's mass, its initial velocity, the insect's mass, its initial velocity. And now we have a combined mass at the end because the two are traveling together, and we're solving for the velocity of the bird and the insect at the end. We're going to combine terms and simplify and solve for the velocity of the bird and the insect, and we get a final velocity of 4.8 meters per second. So you can see that the bird started at 6. When it ate the bug, it slowed down to 4.8 meters per second. The second question is, how much energy was lost in this collision? So for these problems, we're going to look at kinetic energy. We're not going to consider any change in potential energy, but just what was the initial total energy of the bird and the insect, and then what was the final energy of both together. So what we're going to look at is the energy lost. The energy lost is our initial energy, whatever we started with, which is going to be greater, minus our final energy. Our initial energy is our kinetic energy of the bird initially, plus, and that's 1/2 mv squared, because that's what kinetic energy's equation is, plus our initial energy of the insect. That's all the initial energy. And all of that minus the final energy, which is the kinetic energy of the bird and insect together at the end. We're going to plug in our values. It didn't fit on one line, but this is our initial energy of our bird plus our initial energy of our insect minus the combined mass, the energy of the combined bird and insect. And we get values for our energies. Simplify it, and we get that the energy that was lost was 6.32 joules of energy.